propagation methods to real Aeroengine duct geometries.
Thank you very much. And thank you for putting me just before lunch. That's always the hated person standing between all of you and your food. Yes, I'm Alec Wilson. I work at the Rolls-Royce University Technology Centre of Gas Turbine Noise at the Institute of Sound and Vibration Research at the University of Southampton. What we do, we're a team of about 30 people, which includes academics, research fellows, PhD students, and we do research into making jet engines quieter. So we take all sorts of sources of noise on a jet engine and try to make them quieter. We deal in prediction, in measurement, and also in mitigation. Now, I myself spent 30 years in Rolls-Royce. During that time, I worked in aerodynamics and I worked in acoustics. And just 4 years ago almost, I hopped over the fence to work in academia, but still working with Rolls-Royce. So I have some experience, but most of my experience is industrial rather than academic. This is the outline of the talk. While you're reading it, I'll just say a couple of things about this. When Jane asked me to do this talk, initially she said, can you talk about complex analysis in the aero industry? And I don't think my experience is wide enough to actually do that. But I thought I'd say make a couple of comments from my own experience. But in fact, what I want to say is pretty much exactly what Sanjeev has already said, which is that if you look at the mechanics of doing complex analysis, integrating round poles, etc., not many people do that inside Rolls-Royce. That's the 1% that Sanjeev was talking about. So mostly it's wrapped up in methods. So where do those capability developers sit? Well, some of them sit within the company, so that's the 1%. Some of them sit within commercial software houses. So Sanjeev mentioned Actran. Rolls-Royce use Actran, we use Actran, and they have capability developers behind them. But at least in Rolls-Royce's world, Rolls-Royce has a string of these university technology centres, of which we're one, looking at all the different types of problems that they have, and many of those capability developers sit in those university technology centres. So we develop some methods that include complex analysis that go into Rolls-Royce, and Rolls-Royce use them. And today I want to tell you about a method that I'm trying to develop, and you'll see I'm partway there, partway not, and get used in industry. So if you have a fantastic new method based on complex analysis that you want to get used in industry, you can't assume that industry has all these people who are skilled in complex analysis in order to actually apply it. So you need to wrap it up for the end user that Sanjeev was talking about. So we're going to talk a bit about that in the context of this one method that I've been developing. Okay. So this is the target. This is the fan. This is the front end of a jet engine. And here is an intake. And we're looking here at a snapshot of the pressure field upstream of the fan. So the fan's going around faster than the speed of sound at the tip, slower at the hub. We call that transonic condition. And that means that we get shock waves coming off the front of the fan. And you can see the shock waves here. The shock waves spiral along the intake, and then they go out of the intake, disappear to the far field, and that's a sort of whiny noise that you can hear when an aircraft's taking off. So we want to model that, and we want to model it using a nice fast system. But Rolls-Royce can already model it. This paper here by Martin Doherty and Hoang Nam Goong, this was based on a calculation done in standard aerodynamic CFD. So I'm trying to do something that Rolls-Royce can already do. Now, if I'm going to do that and get it into industry, it has to be better in some way. And better in some way for this sort of calculation usually means faster. And it usually means slightly more approximate. So can I make some small approximations that don't affect very much the noise coming out that allows me to use complex analysis on this problem? There was a question earlier about where the gaps are in complex analysis. Well, sometimes maybe we can go back to some old type complex analysis that's made possible to apply in the more complex situations using computing that's available that wasn't before. And that's where I'm heading with this. It is a complex problem, though. Okay, it's a non-uniform duct. You can see at the bottom of the duct is different to the top, and that means that the mean flow is non-uniform as well. So it's a difficult thing to apply a standard complex analysis to. Just to say as well, the non-uniformity of the mean flow comes about from the duct shape, from any incidence that's onto the engine, also boundary layers. Now, boundary layers don't affect the propagation of sound tremendously. This isn't quite true, but for the moment, let's just assume that's true. So boundary layers are going to be out of scope. These are potential disturbances if you ignore the boundary layers, because it's potential flow in here, so both the mean flow and the disturbances are potential. I'm going to model them as Euler disturbances. So that's solutions of the Euler equations around the potential equations, which means that there are, in fact, vortical disturbances in there that I'm going to ignore for this purpose. It's also non-linear, and it's non-linear because we have very high pressure signals close to the fan. I'm not going to cover that in this talk, but I've given some references at the end where I've started to look at nonlinear effects. I'm not looking in this talk at radiation to the far field or the acoustic liner, but again, I've given references at the end. But I want to use an eigen method for this. Okay. So I'm going to build up to the state of the art in terms of eigen methods for ducts and acoustic propagation in ducts. And I'm going to start then with a simple cylinder. And the eigen solution for that is well known. It's a separable solution. So it's a Bessel Fourier harmonic, which means that we have a constant, and this is for the pressure in the duct, times a Bessel function radially, a Fourier harmonic circumferentially. We're at fixed frequency, which we've been through most of today. And the dispersion relation from the wave equation in there allows you to calculate from those numbers a kz, and that kz determines the way that the phase changes as you go along the duct. Now, I should mention in passing, if you're not familiar with this sort of thing, that kz can be real or it can be complex. If it's real, then it's just a phase change along the duct, and waves with real kz's propagate at a uniform amplitude. If it's complex, then we have decay in the direction that the wave's going. We call those cutoff waves, and they decay exponentially along the duct. And that is quite important in an eigenanalysis, as we'll see. Stuart Rienstra from Eindhoven developed that method into slowly varying ducts. And I put one that's slowly varying, but sort of conical, but it could be sort of wavy. But that's an improvement because it gets us closer to what the Aeroengine really looks like. And one of the key things, of course, is if you're trying to get a method into industry, you have to tackle the problem that they're interested in. And by and large, nowadays, industry are interested in three-dimensional shapes. So a two-dimensional method is not going to help even their prelim design. You need to go to three-dimensional. So this is a step in the right direction. Bramley and Peake here did the same sort of thing, but with a curved duct. But the duct had to be of circular cross-section in order to use the right types of eigenfunctions. And then Rienstra again said, well, we don't need to calculate our eigenmodes using Bessel Fourier harmonics. We can calculate the eigenmodes numerically, and that allows you to calculate a duct of general cross-section. So that's heading towards the sort of thing we want, but none of them look quite like this. And there are various reasons. I mean, it is a very complex shape, but also you see there's some scarfing. The tip's further out there than it is here. And using axial planes for analysis is going to make things very, very difficult. So, what are we after then? We're after an eigen-based method that will work for a general duct, or let's say at least a smooth duct. I don't want too many sharp corners. And general mean flow. So here's a general duct. I've made it annular because I like annular ducts. And you'll see later on when I've got a cylindrical duct, I actually use an annular duct. Cheating. Anyway, I'm using this general duct, and I'm going to use general curvilinear coordinates in order to model this general duct. And then I'm going to look for a local eigen solution on one of these zeta planes. So zeta goes along the duct, and I'm going to look at a zeta, constant zeta surface, which isn't necessarily going to be a plane, and then I'm going to look for a local eigen solution. And broadly speaking then, I'm going to propagate waves by moving from analysis surface to analysis surface, and I'm going to use change of basis at each time in order to work out how the wave propagates along. So that's where we're heading. In the eta direction, I'm going to use a spectral method, but it's spectral in eta, not in theta, because eta can also be wavy, bendy. But please note, I'm not looking for an approximate separable solution, because there are papers out there that do that, which is fine in some circumstances, but I'm looking for one that has all the right cross terms in to get a representative solution. So I already mentioned I'm using the Euler equation. So this is the isentropic linearized Euler equation in terms of momentum and mass. And I've put it already in general curvilinear coordinates, which means that it looks more complicated because we have these terms here, which come from the metric tensor, which comes from the Jacobian of the rate of which real coordinates are changing with respect to the coordinate system I'm using. And that makes these quite big. So I actually use symbolic manipulation at the beginning to work out what all the linearized terms are from these equations. And having worked out what the linearized terms are, I can then convert them at each analysis surface into a standard eigenvector form, which is some matrix times df by dz equals another matrix times f, where f is all of the pressures and velocities on one of these constant zeta surfaces. I'm not going to say any more about the method, but that is in that reference if you want to see it. In terms of propagation then, conceptually it's like this. I have a wave coming from analysis surface 2 in that direction towards analysis surface 1. I look at the midpoint, and in this region up to the midpoint I use the eigenvalues from analysis surface 2 to propagate to the midpoint. At that point I do a change of basis from the eigenvectors I've calculated here to the eigenvectors I calculate here. So that scatters the sound field, and then it move on using the eigenvalues to analysis surface 1. Of course, there's reflection as well. And one of the key points of the method is that all of that, the scattering, which you get from the change of geometry and the change of mean flow, and the reflections that you get, for instance, from the area change as you go along the duct, all of that is contained in this change of basis. So you don't need anything clever in order to do this. All you need is to do a change of basis. Now, in reality, of course, we've got sound coming this way and reflective. We've also got sound coming this way. So this is conceptually what you do, but in practice, you need to tackle both of those at the same time because they both contribute to this wave and that wave. So you end up with a very large matrix which covers the whole thing. And that's what I call the global matrix solution, but I won't go into details. Now, being an engineer rather than a mathematician, what I did was, before I started looking too much at the maths, I started looking at whether it would work or not. So I'm going to show you a series of validation cases. What I'm now doing is going back and more seriously looking at the maths and working out what the errors are. But I'm going to show you some validation because that's a bit more fun. This is a Tractrix horn, which is a type of horn. So you put your loudspeaker here, and then this is the horn shape. It's axisymmetric, so it's easy and quick as a test case. And also these guys, Post and Hickson, had already done it. This is the mesh I use for my calculation. One of the things you'll note is that it's a lot coarser than a CFD type mesh would be, or a CAA computational aeroacoustics mesh, at least with a low order computational aeroacoustics code. And one of the reasons this method is much faster than the CFD I showed you at the beginning is that because I'm using the eigenvalues to propagate from one surface to the next, I can take quite big steps along the duct. because I don't have to have so many points per wavelength, which I would need with a fully numerical solution. That's one of the reasons it's faster. Another reason it's faster is that I've got this spectral method circumferentially, which we'll come back to later. The results here are the impedance, resistance and reactance at the speaker itself, and the green line is what you get if you, what I've called a one-way sweep method. What I mean by that is you just start from here and move out this way and ignore any reflections. So if you ignore any reflections, you get the green line. If you include reflections, you get these blue points. And I'm sorry, I apologise, I haven't shown you, but if you look at this paper and you overlay their results with these results, you get exactly the same. So the thing actually works. And what that shows is that change of basis is actually sufficient to capture all of the reflections in the horn. This is perhaps even a simpler test case because it's this time axially uniform, and I've shown you a cross-section of a duct that isn't circular. This is the mesh that I'm using, and I've put in a rather strange pressure pulse, but just over a part of the domain, and I've propagated that along a metre or so of duct. And I've done it with this is the Eigen analysis in general curvilinear coordinates. That's a new method, EAGCC, and I've done some validating CFD, which was done in Fluent, and I get pretty much exactly the same. I won't leave it up too long because you'd see the tiny differences and then ask me about them. Except you won't because it's lunch after me. This next one is a circular to square transition. So I've got a quarter duct here. It's symmetric in the, so I'm just modelling a quarter duct, but it's a part of a full duct. And I'm going from a circular cross-section to a square one. Now this is quite difficult for the method because remember I'm using a spectral method circumferentially. Nonetheless, the results are pretty good. I was quite surprised really. So this is the validating CFD. This is the mode that I'm putting in, so quite a high mode this time. And as you go along, it moves from these Bessel-Fourier to, in the end, you have to use Fourier to get something like a conventional Eigen analysis at this point. So this is a snapshot of the pressure, and if you look, it's really not bad. It's not exactly perfect, but again, we'll skip quickly on. This is a more realistic case, but it's actually symmetric still, and it's an axisymmetric inlet, and I'm comparing this time with the Actran code that Sanjeev and I have both mentioned before. So this time you can see the waves coming along the outer wall and then disappearing off into the far field. These are small amplitude waves, so it's all linear. Actran deals with linear disturbances only, so does this method as it stands. And you can see the results there are pretty well exactly the same, so that's good. I can do an axisymmetric case. This is just demonstrating I can do a lined case. Everything I've shown you so far is hard wall, but with an acoustic liner, Actran gives you this line of amplitude, this is, against axial position along the wall. So the rate of decay predicted by Actran is the same as the eigenvalue method. So you can do lined walls as well. Right, now we're coming on to the actual test case that I started with, and this is the target. So it's three-dimensional. I'm not trying to model the fan. That will be too hard with this type of method. So I'm modeling from that line forwards. However, because this bit's non-linear, and I'm only showing you the bits that I've done on the linear side today, I can only actually model this part of it here. So the pictures I'm going to show you are just the front end. This is a mean flow. It comes from this calculation, but you'll note that it's nowhere near, it's pretty smooth. So in fact, you can get a mean flow with a much cheaper calculation than this. The whole point of this method is that this calculation here, if you just take the inlet, to get this level of accuracy, it takes about 33,000 core hours on a computer. So that's a lot of time and it's expensive. Whereas the method that I've got takes about 1% of that. And just while I'm passing, that is what you need. You need to have, if you're going to persuade industry to use a complex analysis method rather than a brute force method, you have to be down at the 1%, because you've got to think to yourself, are they going to employ somebody to learn your new method, or are they just going to buy more compute power? That's the balance that industry has to make. So this is the mean flow. You can see it actually varies a lot from 0 when you're outside the duct or almost 0, up to 0.7, and you can see that the top and bottom are really quite different with respect to mean flow. So as the waves move along, they'll be scattering radially and circumferentially at the same time. This is the mesh that I'm using. I've mentioned that I'm using a spectral method circumferentially. BPF here is blade passing frequency, and at the lowest frequency, first blade passing frequency, I don't need many spectral harmonics. And this is predicated on the fact that the nacelle itself is fairly close to circular. So if you imagine a mode 18, which is the number of blades coming in, and then you've got something that is non-circular with mode 1, it would scatter from mode 18 to 17 and 19, and then if you went a bit further, it would go to 16 and 20, and if you went a bit further, it would go to 15, 21, etc. So it spreads out from that mode, but it doesn't get very far. I'll show you a picture of that in a second. But at 2 BPF, you need more, and at 3 BPF, you need more. So this method works up to 3 BPF. The thing which takes the time in my method is the eigensolve. And eigensolving is very nonlinear in terms of time. So what you find is you're fine, that takes a bit of a long time. If you try to go to 4 BPF, it would never come back at all. So there's a limit to how big a computation you can do with this method. Actually, I don't have time for this, so I will skip quickly on, but this is showing, I'll just show you one of them. First blade passing frequency, this is the CFD solution at the end of the duct. So you can see that mode 18 is here, and it's spread out from mode 18 to minus 22, and then whatever it is here with 11 harmonics. So I've only used those harmonics, and that again makes the method faster. Does it work? Well, yes, it does. This is a snapshot of the pressure looked at from the side at first blade passing frequency, where you'd expect it to be most accurate. This is the eigenvalue method. This is the CFD, and the two look pretty well bang on. So that's good. Does it always work? Let's skip over that one. Does it always work? No. This is the same thing at 3 BPF. And if you look in this region, it's really not bad. It's really not bad here. Quite good. But at the top here, there's something going on at that top end, which is that we end up with some spurious noise coming out at the very top. And I believe that's due to mode sorting errors. Now, I'm going to talk a little bit about that, and then we'll move on to conclusions. The method is predicated on knowing which way information's going. All that bit about you have a wave coming this way, and then it gets scattered and then reflected and forward, and waves coming this way. If you don't know which way your modes are pointing in terms of information travel, you're not going to get the right result. And if you get one the wrong way round, you can be in real trouble. What I've plotted here is the wave numbers. They're actually pseudo wave numbers. If this were a regular duct, there would be wave numbers in Z, but because we're looking at different analysis surfaces, they're pseudo wave numbers, because I'm looking for something that stays the same shape with respect to e to the minus I k zeta zeta, where zeta is this wavy curvilinear coordinate. But nonetheless, this is an analysis plane 1, which is this one here. So it's quite a funny plane. It's not just an axial plane. But even here, you can see the same structure as you see in the cylindrical duct case. And if you're not familiar with it, what we're looking at here is the well, let's deal with the real part first. The real part of the wave number tells you the phase change as it goes on, and these ones here with no imaginary part are the cut-on waves. So they're the ones that carry on at constant amplitude. The ones with non-zero imaginary part are cut off, so they decay in the direction of travel. And these ones out here are vortical waves that don't really play any part in this calculation. But if you mistake one of these for one of those, then you can be really in trouble. And in this case, it's okay at 1 BPF, but at 3 BPF, the two overlap. And the reason I've got so many points here, of course, is we've got all of the radial modes and all of the circumferential modes all lumped into one. So it's much harder here. Now, I have a better method of doing this now than I did then, And I can do it sort of pretty well most of the time by hand. So I can look at these charts separating out the different modes, and I can work out which is upstream, which is downstream reasonably well. But that doesn't make a robust method that I can give to Rolls-Royce or any other industry, because there's no way that an employee of industry is going to sit there and look at 20 sheets of different modes and just try to spot the one that's wrong. And I haven't worked out how to do this robustly. What I'm trying to do is differentiate my waves into upstream, downstream, and then high order, because I know that a lot of the waves will be like this in terms of where you are radially, for instance, and those modes will never be representative of what's happening physically. So I know there's some high order modes which are poorly captured on the mesh that I'm using. Now I keep those in the calculations because I want a complete system of eigenvectors. Other people have used eigenvector matching. I prefer to have a complete solution to the numerical case, even if I don't have a complete solution to the analytic case. So I want to keep them into the calculation, even if I then discard them. But when it comes to classifying these, I can do that for low wave numbers, because they look just the same as duct modes. But when you get close to these high order ones, it can be very hard to classify them. And remember that because the mean flow is not uniform and the geometry is not uniform, you can have waves that actually increase in amplitude in the direction of propagation, because all of that's part of the scattering that's going on. So it's hardest for high wave numbers. I've looked at group velocity, and group velocity actually has the same issue. Because the modes that I'm uncertain about are modes which are not well captured, the group velocity can be all over the place as well. I don't know the answer to this. If I can't solve it, it'll still be very useful as a research method, and we're already using it for some really interesting things, but I won't be able to get it into industry. Ideas welcome. Please talk to me at lunch. So conclusions then. Well, I've demonstrated it for a representative hard wall case and a lined case. I showed you at least axisymmetrically, and I can cope with non-axisymmetric geometry, non-uniform mean flow. I get very good results at 1 BPF and actually acceptable results at 2 and 3, particularly if you're comparing A versus B. And that will allow us to look at, well, what happens if you move the duct around a bit? What happens to the noise in the far field? The lack of robustness is an issue, particularly with regard to getting it into industry. The compute time is less than 1% of the CFD solution. That's up to 3 BPF. As I mentioned before, if you try to go up to 4, 5, 6, then the method just stops dead and your computer just blinks at you happily. That's also, incidentally, why I can't handle boundary layers in this simulation, because to handle a boundary layer, you need a lot of mesh points in that region. So in theory, it works fine. In practice, it raises the size of the problem to a point where the computer just won't handle it anymore. I'm just about to finish. Last thing I want to say, if you look back, if you take a step back and look at why the method's fast, I've already mentioned the fact that you can have large steps in delta Z, so you don't have a points per wavelength issue like you do with finite difference or standard CFD solvers. I've already mentioned the spectral aspect of it, which is that we don't have to calculate every point around the domain. We can use a restricted number of circumferential pseudo-harmonics. There's a third reason as well, which is that because every analysis surface is treated individually, it's trivial to parallelize. So if I want to cut down the analysis time, I can send each surface to a different processor. So at least to get to that point, it's trivial, and that's why the time is so impressive looking. Thank you.
So when studying those problems, are there situations when double precision is not enough and one should use higher arithmetic precision?
I think there are bigger errors than that. The most difficult point is where you have a transition from cut on to cut off, and I don't think that higher precision would help.
Do you need a special technique because your flow's transonic as opposed to subsonic or supersonic?
The rotor's going supersonically or transonically through the flow, but the flow itself is subsonic. The mean flow is subsonic.
That makes life a lot easier.
Yes, absolutely.
Proper transonic hyperbolic.
Yep. Yep.
Okay, thank you.
Question I would usually ask is, what do you believe in CFD? So when you do that comparison and find those differences, how do we know that they're not artifacts of either of the methods?
It's a good question. There are some cases that I've done where I don't believe the CFD. If you're looking at tone noise, where I think it's generally accepted that the viscosity plays a relatively small part, you're then down to the definition of the CFD. And we've done a lot of work, in fact I did this when I was at Rolls-Royce, we've done a lot of work analysing exactly what mesh size you need to propagate different tones over certain distances. Even so, there's often a 1 dB decay. And in that case you say, well, that's obviously the CFD that's wrong. But you don't generally get really weird things.
The Z variation that you are ignoring, you put it in the eigenfunction.
Yep.
You have e to the ikz. A itself could be slowly depending on Z.
Yes.
So does that become important in your...
Yes, well that's one of the big sources of error. It's difficult to, it would be very difficult actually to have k as a function of z to integrate it, because your actual modes are changing as well. It's not just the eigenvalue, it's the eigenvectors that are changing too. Yes, yes, but remember that I'm tracking all of the modes, and actually finding which mode here relates to which mode there is itself a problem in its own right. So it's very difficult. But what is true is that you can, I believe, quite easily look at the changes from one plane to the next and work out from that what your second order error is going to be. Because it is a first order error, because I'm integrating in a sort of first order way.
Right, so let's save the remaining questions for the lunch break, and let's thank Alec again.